All right. I wanted to finish up this unit with just telling you some definitions and facts about sequences here. All right, so instead of writing these all up by hand, we'll just sort of read these and talk about these. Um, so this theorem here, we've actually kind of already talked about this. But let's say, we have an explicit formula for a function here. If we turn that function from a discrete function, in other words, a function that only can take in integers as values, to a continuous function, f of x, right, or a function defined on the whole real line, at least, then if we take the limit of that function as we go to infinity, that's also what the limit of the sequence is. So actually, let me just go back and write one thing here. This example we did earlier, where an was negative 1 to the n over n squared plus 1, right? An example of a function f of x that would work here, say f of x, right? The bottom, we'd obviously want this to be x squared plus 1. How do we emulate this negative 1 to the n? Well, we can do this with sine and cosine. Right? So here, let's see, when we plug in n equals 1, we want to get negative 1. So a good candidate here would actually be cosine of n pi. Right? Because if you think about what cosine of, sorry, not n pi, pi x, pi times x. Let's write it that way. Why is that? Well, let's think about n values and cosine nx values. When n is 0, it's cosine of 0, which is 1. When n is 1, it's cosine of, sorry, not nx, this should be n pi. Right, that's cosine of pi, which is negative 1. When n is 2, this is cosine of 2 pi, which is 1. When n is 3, it's cosine of 3 pi, which is negative 1. So in other words, cosine of n pi is exactly equal to negative 1 to the n. And so likewise, if you wanted negative 1 to the n minus 1, you could say, cosine of n minus 1 pi. That's one way to do it. You could also just say negative cosine of n pi. That's probably the better way to do it. Right? But this right here is a very useful fact for turning sequences into functions. Right? So, yeah, so if we were trying to make a continuous function out of this, we would turn it into this. Anyway, back to the definitions here. All right. So yeah, so that's the idea here. We take our sequence and we turn it into a function and we take the limit of it. So really, we've kind of already talked about how to do limits of sequences last semester. Okay. Sequences follow some limit laws that you would expect them to and hope for them to, right? Right? These are the same kinds of rules we had for limits of functions. If we add or subtract two functions, then take the limit, we could just take the limits first and then add or subtract them. If we take a function and we multiply it by a number, then the limit of that would just be that number times the limit of the function. And so on. If we multiply two functions and take the limit, we get the product of the limits. And if we divide two functions and take the limit, we get the quotient of the limits, as long as the bottom one doesn't go to 0. Right? So again, everything that you sort of expect to happen, happens. Right? Now, here is some important definitions here. So, these are technical terms, but the last two are actually quite important. So let's talk about these. Right? So an increasing sequence is a sequence whose value continues to go up no matter what, right? Every term must be bigger than the previous one. That's an increasing sequence. right? Now, along with an increasing sequence, we have what's called a non-decreasing sequence, right? What this means is the sequence can stay the same or go up, but it can never go down in value, right? So you could have a sequence that's like 1, 2, 3, 3, 3, 4, 5. That's fine. That would be non-decreasing. But 1, 2, 3, 2, 3, 4, 5 would not work because it went down at some point. Right? And then likewise, along with the increasing terms, we have decreasing and non-increasing. Right? So a decreasing sequence is one where every term of the sequence must get smaller. Right? It has to get smaller no matter what. So everything must always be smaller than the previous term. And non-increasing works basically the same way as non-decreasing, right? It's a sequence that can sort of be the same or go down. So for example, 5, 4, 3, 3, 3, 2, 1 would be non-increasing. But 5, 4, 3, 3, 4, 3, 2 would not, because it went up and then back down, right? So the idea between our for non-decreasing and non-increasing is to say, basically, if the sequence is changing, it's either only increasing or only decreasing. That's sort of the idea, right? Now, all of these up here, all 4 of these types of sequences are examples of what are called monotonic sequences, right? And again, a monotonic sequence is just saying, you know, it has to trend upwards always or trend downwards always, right? Now, the reason monotonic is important is because of this next definition, bounded, right? A sequence is bounded if it's kind of always stuck between 2 values. So let me draw a picture here for you for bounded, to kind of give you an idea of what that looks like, right? So let's say here's, you know, some axes here, right? So how does this work? Right, so here, let's say we have some monotonic sequence, like this. Right? And here we're saying, all right, here's a value that it never crosses. Right? So if this is m, then down here would be minus m. And what we're saying is that all of the dots in the sequence are between these 2 lines. Right? So between m and minus m, every value of your sequence is between those 2 numbers, right? For some number. Okay? That's what it means to be bounded, right? Now, if it's also monotonic and bounded, like here, let's say, you know, this is, let's just call this non-decreasing here. This looks like it might actually just be increasing, but let's be careful and just call it non-decreasing. So what do you think you can say here? If the sequence is bounded, meaning that it's stuck between these 2 red lines, and it's non-decreasing, so it has to keep going up or stay the same, what do you think's got to happen as we go to infinity? So what sort of has to happen here is, you know, since I can never get larger than this value m here, then at most this sequence can take on the value m and nothing larger, right? It might not actually get up that high, but the point is that caps it off. And if the values are only allowed to trend in one direction, what that means is our sequence can't wander off to infinity, right? And since it's monotonic, it can't bounce back and forth. That actually means it has to converge. So that gives us the next theorem here. a bounded monotonic sequence converges, right? So that argument we used works for a sequence that's increasing, or sorry, non-decreasing or non-increasing, right? So a function that's monotonic and bounded has to converge, right? We don't necessarily know what it converges to without doing some work, but we know immediately that it has to converge, right? And one last thing I want to write here is this thing called the squeeze theorem for sequences. So you might recognize this from the squeeze theorem for functions, sometimes called the sandwich theorem. We're not going to use this too much, but I just wanted to point this out. That's kind of saying, like, if we have a sequence that we're interested in this case Bn, if we can put a sequence below it and a sequence above it that both converge to the same spot, then the sequence in the middle is sort of sandwiched or squeezed to the same value. Okay, so that's it for the technical bits there, and I'll see you next time.